Okay, so now we're going to do our homework solutions for chapter 10.2, questions number 16 through 23, starting with 16, and that's on page 318. Find the mass in grams of 4.52 times 10 to the negative 3 moles of C2H42, C20, excuse me. So we're looking at C20H42. Wow. And we're looking at 4.52 times 10 to the negative third moles. So the first thing we need to do to find the mass in grams is we need to find the molar mass of this compound. And that molar mass is going to equal 20 times the molar mass of carbon plus 42 times the molar mass of hydrogen. And we know that's going to equal 20 times 12.0 grams per mole. Don't forget those units. Plus 42 times 1.00 grams per mole. And that total right there is 240 plus 42 equals 282 grams per mole. Now, we're going to be using this over here somewhere. Let me rewrite this a little bit lower. 4.52 times 10 to the negative 3 moles of C20H42. Put it over 1 because we're going to be using conversion factors. Makes it easier to work with. And we know that this compound weighs 282 grams per 1 mole. That mole cancels. That mole cancels. Now we're just left with 282 times 4.52 times 10 to the third. And the answer is 1.27 grams of C20H42. Number 17, we're told to calculate the mass in grams of 2.5 moles of iron 2 hydroxide. Now, a little bit of practice here. We were talking about iron 2 hydroxide. Gives us a chance to practice our ionic bonding and polyatomic ions again. Iron 2 means that we have a +2 oxidation. And hydroxide, we know it's OH, and it's a -1. So how do we get this to balance? We take this 2 right here, and we put it here. And we take this invisible 1, and we put it there. And we end up with the following compound with correct subscripts. Iron, you're going to have your hydroxide, then you got 2 of them. Great. I suspect we're going to need to find the molar mass. So the molar mass of this iron hydroxide. 1 iron, all right, that's supposed to be an iron, plus 2 oxygens. There's a 2 subscript right there, 2. So we got 2 oxygens plus 2 hydrogens. Iron has an atomic mass of 55.8. One of the units, grams per mole, correct, plus 2 times 16 grams per mole for the oxygen, and 2 times 1.00 grams, sorry I squeezed it in, moles for the hydrogen. And when we work out this molar mass, we're going to get something like 89.8 grams per mole. That's the molar mass for iron hydroxide. Now, we're asked to calculate the mass in grams of 2.5 moles. So if we have 2.50 moles of iron hydroxide, and we multiply by 89.8 grams per mole, 1 mole of this iron hydroxide. Oop, that's supposed to be in parentheses. Sorry. Try that again. We're going to get, I'm going to move this so it doesn't look like that's the answer. And our answer to this question is going to be 2.5 times 89.8. Moles cancel here and here, and we're left with 224. Let's keep those units, those significant figures. I'm going to have 3 significant figures. 225 grams of iron hydroxide. Number 18 and 19 are similar to 16 and 17. What we're looking for, we're going to go in the other direction. Instead of starting with moles and finding the mass, we're going to start with mass and find the number of moles, specifically in 3.70 times 10 to the negative 1 grams of boron. Now, let's use that molar mass, but let's use it in the inverse. You've got grams here. We'll need grams on bottom. And we want to calculate the number of moles. So we'll need moles on top. So we'll get how many grams of boron per mole. Well, boron has atomic mass units of 10.8. So that's how many grams per mole of boron. And the grams cancel, just like that. And we're left with 3.70 times 10 to the negative first divided by 10.8 equals 0.343 moles of boron. Now, did I keep the right number of significant figures? I used 3 here, and I used 3 here, and my answer has 3. However, I do believe I made a mistake with my decimal place. Let's try this again. Does that look better? Looks better to me. So we have 0.0343 moles of boron. Let's do 19. I suspect it will be similar. Calculate the number of moles in 75 grams of dinitrogen trioxide. Now there's one of those covalent naming opportunities. Let's review that. Dinitrogen, that's N2. Trioxide, O3. These are both nonmetals, therefore this is covalent bonding. You don't need to worry about the oxidation numbers. You have the correct formula. Let's calculate the molar mass. It will equal 2 times the molar mass of nitrogen, which is 14.0 grams per mole, plus those 3 oxygens, 16 grams per mole. Altogether, that's 28 plus 48. Looks like about 76 grams per mole of N2O3. Now, we're told that we're starting off with 75 grams of nitrogen trioxide. I'm going to move on down here. All right, too far. And there we go. 75 grams of N2O3. Put it over 1 so I can remember I'm dealing with fractions. Now, I need to find how many moles of N2O3 I have. And to do that, I need to multiply by a conversion factor. Now, we're going to use this molar mass that we calculated over here. However, we're going to have to use the inverse of it. We're going to have to use grams on bottom so that this gram over here and this gram will cancel, and we'll have moles on top. So if we have 1 mole of N2O3, that will weigh 76 grams. It's right here from the molar mass we calculated. Okay, we just turned this upside down. We converted it. Okay, and grams cancel, and we end up with pretty much 1 mole, 1.0 mole. In fact, let's just see what we end up with when we calculate. That's 75. Let's make sure we have the right number of significant figures. 75.0. And when we did this, we had 76.0. So we'll have 76.0 over here. We'll need 3 significant figures. So when I divide 75 by 76, I get, let's have a little more room, 0.987 moles of N2O3. Okay, moving on ahead, we're going to go to number 20 and 21. Now these two problems are going to make use of the mole to volume ratio. 22.4 liters. That's the volume of 1 mole of any gas. Okay? And if you'll recall, we can take 2 conversion factors out of that both equal 1. We could use a conversion factor like this, where we divide both sides by 1 mole, or where we divide 1 mole by 22.4 liters. These are your 2 conversion factors that we're going to use on these problems. Here we go, number 20. Let's see how this breaks down. You've been asked to calculate the volume of these gases at STP, standard temperature and pressure. 1 atmosphere, 0 degrees Celsius. That's standard temperature and pressure. Number A. Well, we got 3.2 times 10 to the negative third. Moles of CO2. Let's just start right there. And draw a line under it and put a 1, remembering that we're always dealing in fractions when we're doing conversions. And which of these 2 should I use? I'm trying to find volume. I need to have moles on bottom so that this mole and this mole will cancel, which means I'm going to use this conversion factor. I'm going to multiply by 22.04 liters, and I will get liters as my volume. 7.1, I'm going to do it not scientific notation, 3.2 into the 3 negative, 22.4, and I get 0.717. Make sure you keep those significant figures. Okay, just to speed things up, I've already done B and C. It's the same calculation as in A. You're just multiplying the number of moles times 22.4 liters per 1 mole. Moles cancel, and you're left with your volume in liters. Now I have a sneaky suspicion that on 21, A, B, and C, we're going to be doing just the opposite. Instead of multiplying by 22.4 liters per mole, we're going to be dividing by 22.4 liters per mole, or multiplying by the inverse, which is 1 mole over 22.4 liters. And let's try it. 67.2 liters of SO2, sulfur dioxide. Just to make it easier, I put it over 1, and now I'm going to have to invert that molar volume. Put 22.4 liters on bottom and 1 mole on top. Liters cancel. I'm left with 3 moles. 3.00 moles of sulfur dioxide. Okay, for expediency's sake, we've skipped ahead in our broadcast, and there's B and C as well. And again, we're just multiplying the volume by 1 mole over 22.4 liters. That's your molar volume right there. And you get moles. The cool thing about this is it doesn't matter if it's little old 4 grams per mole helium, or if it's something much heavier like ethane. It still takes up the same amount of volume, and that conversion factor of 22.4 liters per mole still works. Okay, 22, a little trickier. They give us a density of a gas that's made out of sulfur and oxygen. Density is 3.58 grams per 1 liter. And we're told to find the molar mass of this gas. Now, interestingly enough, we got liters on the bottom and molar mass. The units of molar mass is grams per mole. So what do we do to get the grams per mole if we have grams per liter? It's very simple. To get this liter right here to cancel, we need liters on top. And to get moles on bottom, like we show over here in our answer, we'll need moles on bottom here. Is this starting to look familiar? Liters per mole. If we have 1 mole, then we have 22.4. Aha, there's our mole volume relationship again. Our mole volume relationship again. And all we have to do is multiply by 3.58 by 22.4. The liters are canceled, and we're left with grams over moles. And rounding to 3 significant figures, we get 80.2 grams per mole is the molar mass. Moving on along, let's try 22. That was 22. Let's try 23. Now we're just going to do the same calculation in reverse. What is the density of krypton gas at standard temperatures and pressures? Krypton gas, Kr. What is the molar mass of krypton? I'll tell you what I want molar mass. They want me to find grams per liter. You recognize what that is? That is my mass over volume, my broken heart. That's my density right there. And that's what I'm trying to solve for. But all I know is that I can solve for krypton's molar mass in grams per mole. Right? For 1 mole. How many grams does 1 mole of krypton weigh? It weighs 83.80 grams. Now, I need a conversion factor that gets rid of this mole on bottom and leaves me with liters on bottom. I already have grams on top, so I'm good so far. My conversion factor is going to look like L, and it's going to have moles on top. 1 mole, and here we go again, standard temperature and pressure. There are 22.4 liters of gas in 1 mole of gas. Moles cancel, I divide 83.80 by 22.4, and I get a density for krypton gas of 3.74 grams per liter. Notice how I have the correct number of significant figures, and I have my units. And that is it for today's homework.